And we're done. So Martin, over to you.
Okay, thank you very much, Sam. Yeah, welcome to everybody. I recognise a few names and faces in the attendance list today, and I know there's quite a few WebTech distributors listening today, plus lots of new people as well. So welcome to you all. As the title says, we're going to talk about condition monitoring today, how it can be a powerful tool to save or make you money, save money by reducing downtime, or make money by maximising machine efficiencies. We're going to use some real examples, look at some of the challenges that users have had and how they overcame them, and highlight some of the products that can be used. And then at the end, we'll talk a bit about general product selection. So we're going to dive straight in by talking about a particular company, and this company is called Mining and Oilfield Services. So the industry they work in, well, the clue's in the name. It may sound like a real company, but it isn't. For the sake of this presentation, we've created a fictitious company and some people working in it, but rest assured it's based on lots of the experiences and conversations that we've had with customers. So the mission of this company is to have a safe working environment, to be a reliable supplier of choice and provide innovative solutions. And within that company, we have three main characters. Lauren is the leader CEO of Mining and Oilfield Services, and you may recognize Lauren from some previous webinars if you've attended before. And working for him, we have Declan, who's the design engineer, and his mission here is to design faster ways to set excavator pumps, and Steve, who's the service manager, and his job here is trying to keep the mills going despite their age. If we just think a little bit about what the industry is like, here they're dealing with some really massive machinery, 24/7 operation, high value metal ore extraction and processing. Maintenance team have always got too much to do and too little time to do it, and where downtime is often measured in sort of six figures, so $100,000 an hour or more. So uptime is critical. The industry is also potentially very dangerous. The culture is changing. They're trying to reduce exposure by humans to machines where possible, but they're also very focused on hitting their output numbers. So let's talk a bit about the challenge. So Lauren has set this challenge to his team. He recognises that the fleet of machinery they have is aging. He recognises that's potentially causing reliability issues. And he's driving to reduce the amount of time spent on scheduled maintenance, which might sound sort of counterintuitive, but he wants the maintenance team to be as effective as possible. And so for Declan, that is, how can I change the hydraulic circuit to enable quicker maintenance? So they're doing planned maintenance at the moment, but it's often taking days on certain machinery, and going, how could we do that faster? And Steve, who's looking after the industrial plant, how can I keep the machines running longer and keep the costs under control? So we're going to follow Declan and Steve through their various challenges. Let's just look first at how WebTech can help with this. So for over 60 years, we've been helping mobile and industrial machinery OEMs with measurement and control solutions. The applications you can see here on the screen are perhaps typical of this sort of industry, but for WebTech, it could as equally be in agricultural machinery or oil and gas or many other areas where hydraulics are used. Regardless of which industry or which application, we have a four-step approach to finding the best solution for customers. And that four-step approach we called Make It Blue. Make it blue because that's our corporate color, and make it blue because the BLUE stands for begin, listen, upgrade, and engineer. And if you look at what we're going through today, the webinar that we're presenting today is perhaps an example of the beginning, of sharing training material in the industry. The stage after that perhaps is what you're going to see in terms of the examples with Declan and Steve, and the listening to what their challenges are and recommending a best solution. We have many long-serving people in the company with deep experience on hydraulic product design and applications, and together we often consulted on what's the best solution for a particular application, and there we would use a blue scorecard. And from that, we would then look at if that's a suitable alternative, a suitable product, sorry, whether we'd upgrade by making modifications to an existing product and then engineer the final solution, which we then support worldwide. So that's a little bit about our approach, and you'll see a couple of examples of that as we go through the presentation today. So for those of you who've been to a few of these webinars before, you may know of the different maintenance types that we like to refer to. And thanks to Steve Skinner's help here, we've documented these and illustrated them in different ways. And we're just going to refer to them briefly at the beginning because I think it's a good backdrop to condition monitoring. So the four maintenance ways that we have here, the first is reactive. Perhaps too often used in many industries, is wait for it to go wrong and then fix it. The second approach, preventive, estimate when it will go wrong and then fix it before it does. Predictive, monitor its condition and fix it when necessary. And proactive, try to stop it going wrong or minimize the consequences of failure. So in this video, in this presentation, we're going to talk about condition monitoring, and it'll be a combination really of the preventative element, but it may include some predictive elements and even some proactive elements at the same time. So let's start with setting the scene for Declan's challenge. We have a large mining excavator, and here we know that the maintenance team have been tasked with maximizing the efficiency on this machine at all times. The machine operates, as I said before, in a 24/7 environment. In order to do that, they are tasked with tuning the machine sort of every 6 to 12 months. And to tune it, they have to monitor the machine in the field. They're not taking components off it. So we've broken down Declan's challenge. How can I modify the circuit to make maintenance faster? So how can his maintenance team spend less time doing that tuning once or twice a year? And the first challenge they've had is minimize the time to install. And really they want a rugged solution to fit and forget. And why is that important? Well, here Declan's talked about it. He said, I've tasked to provide faster hydraulic pump setup on large mining shovels and drills, where the pump settings on a load sensing pump, maximum flows and pressures need to be checked every 6 to 12 months. And let's just have a look at what that might mean from an application point of view. Here we've got the pump installed deep inside the machine, and there are multiple pumps on the machine, often installed in awkward to access places with limited space. So the first challenge for the maintenance team is actually installing instrumentation in there in order to carry out the tests. And installing temperature and pressure sensors is normally a little bit easier because there are test points that you can screw onto. But when it comes to measuring flow and checking the flow output from the pump, it's more challenging. And using portable instrumentation then involves a whole shopping list of tasks, and many of you within the industry will be familiar with this. To find the convenient hose or location to install the test unit, locating the correct fittings and adapters, and we know how challenging that can be as the industry refuses to standardize on any one particular thread, and we probably have about 10 different standards around the world. Ensuring the system's safe to disconnect, depressurized, engine, the motor's locked out, the fluid is sufficiently cool, and then making sure they've got the right test unit for the flows and pressures they're hoping to measure. There's also concerns when you break into the circuit about minimizing contamination, making sure that the unit's installed correctly. This unit's got a load valve on it, so it's there to restrict the flow and raise the pressure. So we make sure that's open. And then once the whole test has been completed, there's then the whole exercise has to be reversed and the flow unit taken back out again. And then all the connections remade, air bled out of the system, and deal with any spills and any interlocks. So that in itself takes roughly 2 to 3 hours for each test on the pump, and there are multiple pumps on this machine. So Declan's challenge is how do we want to do the scheduled maintenance, we want to tune the system, we want to maximize the efficiency, but we want to do it without suffering this 2 to 3 hour cost of installation. And so what's the alternative? Isn't suitable to leave that particular unit in place the whole time, but what's an alternative approach? And that would be to put in a ruggedized flow meter that can be left permanently in line with a digital output. So we just look at this particular unit in more detail. So this unit, rugged, yeah, so IP69K, it's kind of the highest water and dust protection that you can get on an instrument tested for vibration and shock. This particular one rated for 80 gallons, 300 litres, up to 6,000 psi and 420 bar, and could be connected in a couple of different ways. Originally, this unit was designed for SAE J1939 CAN connection on mobile machinery, and interestingly, quite a number of industrial applications came up, and where users came to us and said, "Yeah, I want that particular unit, but can't you do it with a different output?" And thanks to the Make It Blue approach that I just mentioned, we looked and said, well, why not? Why don't we do that with 4 to 20 milliamp output? You don't get temperature, but you certainly can get the flow signal out of it. And so the signal there could be measured at any time just by connecting in the cable. How does this work? This is a turbine-based technology. It could be used in both directions. That would be calibrated in one particular direction. And as flow passes through the flow monitor, the turbine blade spins. The speed is proportional approximately to the flow rate. That's calibrated and configured within the electronics. And then the electronics gives out a signal via the CAN bus or the 4 to 20 milliamp. It also measures temperature, as I mentioned, but only on the CAN version. See there. So that's the first challenge, if you like. So how do we reduce the time to carry out the test? Well, if we leave the flow meter permanently in place, then we've just chopped sort of 2 to 3 hours out for each test. So conventionally, you might put instrumentation on so that you can permanently connect to it, but you don't necessarily have to, and we'll come up to that in a moment. So the second challenge that Declan's got is how can you then use that instrumentation to set the pumps faster? So on a variable displacement piston pump, there may be various parameters that need tweaking. So we talked about tuning the pump at the beginning. So here it might be adjusting the Qmax or the standby pressures or the compensator pressure on the load sensing pump. And with that flow meter in place, it's relatively easy now to bring along a readout. So in this case, we've got a hydraulic data logger, so the HPM, I think it's 5,000 unit there, plugged straight into the flow meter, so the 4 to 20 milliamp signal coming in, so providing power and signal there. Plug a pressure transducer in. There could be other sensors that are plugged in at the same time, but that allows us then both numerically and graphically to carry out those tests that you see at the top of the screen. So you want to set the maximum flow limiter, the load sense pressure, and the pressure limiter.
Martin,
yeah,
there's 2 questions coming. I didn't know if you wanted to answer them now rather than wait to the end, because I think they might be relevant to the last slide. The first one, it says, is temperature on oil or electronics?
So on the CTA, the temperature, if I understand the question correctly, the temperature is measuring the oil temperature. So that is buried in the bottom of the flow transducer. So as the oil is going across the bottom of that transducer, it is heating up that temperature sensor. So you're getting a very authentic oil temperature measurement out. But as I mentioned, you're only getting that signal out of using the CAN bus. On the 4 to 20 milliamp, it's only got a single signal coming out of it, and so that's just the flow signal.
Okay, yeah. And the follow-up to that, he said, okay, great, probe in flow path.
Yeah.
And one more, sorry, is can the CTA I think be used with, is it mill lube oil 320 viscosity?
That would be a case of a little bit of a longer conversation, I think.
Yeah.
So what
Okay.
we're looking at there is 320 is referring to the viscosity at 40 degrees C, so 320 centistokes. Typically, these in most hydraulic applications would have been calibrated sort of around 20 centistokes. So clearly, there's quite a big gap there on viscosity, and that'd be a case of us doing a bit of a deeper dive, if you like, into your requirements capture and going, okay, so what are the operating temperatures? What's the ranges? What's the allowable pressure drop, etc. So in principle, yes. In practice, we want to kind of dive a bit deeper into it.
Okay. All right. Thanks.
Okay.
Thanks, Martin.
Okay, so we carry on from there. So we've covered the first two challenges, minimize time to install set pumps faster. So the third is the going, well, we've got that information. Could we also use it to predict pump performance? And the advantage we've got is that we've connected in a data logger. And so by its very nature, we have the ability to save that data. So not just display it on screen, but also store it in the device, connect that device to a computer or store the data onto a USB stick, and then take that and analyze it afterwards. So the advantage of that is if you're testing every 6 or 12 months, you've got test data on the pumps. You could store that data, archive it, compare it, and with the help of the software, you could overlay that data and say, okay, so there's the comparison from January, from June, from December, and look at how that performance of that pump or pumps are changing. There may also be a challenge, for example, where you aren't achieving the performance that you hoped or wished for or were told you would get from that pump, and you want to then communicate that to other people. So having the data logger there enables you to actually get the facts at your fingertips, and then send that data on to maybe the OEM who made the machine or who built the pump, and ask them for support. And generally, if you've got actual real data at your fingertips rather than, yeah, it's off a bit, it's a much more powerful conversation. If we were to look at how that might work in terms of the pump monitoring, if we think about the performance level of the pumps up the y-axis there, let's assume that's the volumetric efficiency of the pump, and across the bottom we've got the time. Over time, first a few thousand hours, it's pretty flat. You'd expect very little difference. The new pump performance we could indicate by the line at the top, and you could say, okay, over time you'd expect it to get a little bit worse, the pump efficiency, and it will reach a point when you go, okay, that's about as bad or as poor as we want it to get. So we can draw a line, if you like, between where it was when the pump was first installed, and where it is now, our sort of first test in the field. And we can repeat that on each successive test when we go out and carry out the tuning. That gives us the ability to then predict when the pump might fail, when we might have an issue, we need to switch that pump out. If the pump failure suddenly got considerably worse, perhaps due to a contamination incident in the circuit, then you might get a sudden change in that performance, and a catastrophic failure. So from a condition monitoring point of view, you've got a couple of different options here. Had you installed the CTA and connected it straight into the PLC, you could have that data feeding in continuously, in which case you could see everything every second that was going on that pump. That may or may not be that easy if it's a retrofit. If you're carrying out the testing periodically every 6 months, there's a chance you might miss it in between those 6 months, but equally that may be sufficient for you to see the trends on the pump, and see what's happening, and what's likely to happen in the next 6 months. So it's just visually displaying, if you like, the condition, the continuous condition monitoring, and being able to see things all the time. But as I say, for this particular application, Steve doesn't have the opportunity to feed that data back into the PLC on the machine, and is actually quite happy just to be testing it periodically. Steve also recognizes that in order to improve the efficiency of the system, he's made a change to the circuit. He's now got to train the people on how to use the equipment and how to get the best out of it. So the training element of this shouldn't be forgotten. It's fine to have the tools and recognize the changes, but the investment in the training is also important. And so I just want to highlight here, competence training and retraining is vital, and Steve sees that as his next challenge. So on the left-hand side there, you see an example of a book that Webtec's published with the help of Steve Skinner, called Practical Hydraulic System Maintenance, which is available on Amazon, on Kindle and in paper. But equally, if you go to many of the fluid power trade associations like CTOP or the BFPA or the NFPA, they will hold a list of accredited training organizations, and they will also carry out some training themselves in some cases. And we are aligned in the UK with the NFPC, which is the leading fluid power training centre in the UK. And the reason we recognise training centres such as the NFPC is that they focus on competence-based training, not just theoretical trainings. This is very much hands-on, actually carrying out the changes that you want to do in the field. Okay, so if we just look at the 4 challenges we've covered there for Declan, he wanted to minimise the time to install, save potentially 2 to 3 hours for each test. He wanted to set the pumps up faster, so he took a data logger to be able to display the flow pressure and temperature and other settings at the same time. He wanted to predict pump performance, so he took those data logged values, stored them, and then compared them. And then in order to get the maximum out of his whole team, he organised a training course to keep them all trained. So that's Declan's particular challenge. I'd like to move on now is to Steve's challenge on the ore processing plant. So this is a large installation which is covering the movement and crushing of the ore as it comes out of the ground, and the grinding of it on the right hand side. And Steve's challenge is around keeping uptime, so reducing downtime in the plant. And he's aware that his team going out and they're carrying out visual inspection, but actually they haven't got the right tools in place in order to give them a true picture of what's going on inside the hydraulic circuit. Putting a hand onto the hose and feeling how warm it is isn't really a great indicator of whether that pump is operating correctly. And so what he's looking to do is improve the visual management for the maintenance team. This describes it here. To improve the maintenance program for the hydraulic units on the ore processing mills, we want more and faster visual checks of current performance. And so often the challenge around the plant is that on some machines the pumps are difficult to access, which means that inevitably those ones don't get looked at very often. And if they're mounted in inaccessible locations, they can be monitored without removing them from the installation. So again, here we've got high emphasis on uptime, running 24/7. They don't want to interrupt the circuit unless they need to, unless it's really already broken down or imminent failure. And so here you can see a unit installed on top of that tank, which is a flow indicator unit with a temperature sensor built in. Let's take a look at that in a bit more detail. So this is for measuring flow and temperature with a test point on top, and then very easy to add the addition of a pressure sensor. So that could just be a glycerine gauge. It could equally be a digital pressure gauge, such as the one we have here. The unit's rated to 350 or 420 bar, depending on the size. Very strong, suitable to withstand sort of the knocks and bumps within that environment. No cables, so from that point of view it's very easy to install. There's no battery on the flow temperature element of it. Nothing that needs changing, and likely to last for a very long time in that circuit. The advantage of putting a digital pressure gauge on the top is that you then also immediately got the opportunity to monitor for pressure spikes. So if there was a concern in that circuit about why are things failing, then you could take that's an HPM 110 unit there, a little data logger, and just put it on, and you can monitor over 24 hours for any pressure spikes that might be occurring, analyze the data afterwards, and you've got a very good visualization of what's happening inside that circuit. In terms of the unit itself, the flow indicator, this is a variable orifice meter. So the piston you can see at the bottom there has a magnet inside it. This is like a section through the meter, as if you're looking down from the top. As the flow accelerates, it will push the piston across to allow the flow through, and the linear magnet inside the bottom half is attached sort of rack and pinion style to the rotary magnet you can see at the top there, which rotates the dial. Simple but very effective, very good at telling you what's going on in the circuit. Say with no batteries, it's simply using some of the energy from the oil, so it's got a small pressure drop across it in order to move the piston against a spring. And these particular units, so these are installed in the pressure line, allowing you to measure at high pressure what the flow is out of the pump, which is the first place really to focus on if anything's moving slowly. If cylinders or motors are moving slowly within the application, then that would be the starting place to check the pump is delivering the correct flow. The other application, or the other side of monitoring pumps, is whether you monitor case strain. This seems to be quite a topical discussion when we talk to different people. Some people are very much in favor of it. Some people aren't. We sit there going, the solutions exist. I think while there are pros and cons to monitoring case strain, so the pros that are, you can put it into a low pressure line, so it's not a high pressure line. It's potentially a bit cheaper to install an instrument there. It does give you fast visual monitoring of possible issues, which gives you potentially early detection of potential failures. The cons, just to be aware of, the maximum pressure on a case drain is often very low. If you install anything in the case drain line, then you're introducing a pressure drop. So that's hence the note on there, ensure sized correctly for peak flow. The peak flow when the variable displacement piston pump deswashes could be quite high. And if you have something in there restricting the flow, then you could get quite a big pressure drop, which could blow the seal. So generally, if people are specifying a case strain monitor, oversize it slightly, go up a size in order to minimize the pressure drop across it. The other thing is you need to know what good looks like. If you're getting a certain amount of oil coming out of it, but that varies depending what the pump is doing, how do you know when you've got an issue versus the pump is just deswashing at that particular moment? So I think it needs careful consideration by the designer as to whether they put in pressure line monitoring or case strain monitoring. The only thing I will say is that the difference in price these days is narrowing quite a lot between case strain monitoring and pressure line monitoring. So an decision that Steve's taken in this example is it's better to put in the pressure line monitoring than case strain. But as I say, the opportunities to use either exist. Okay, so let's look at the next challenge on Steve's list. So we've talked about the visual indication of the pump. Let's talk about monitoring motor flows. So the device that we just showed for monitoring the pump flow, what we called a variable displacement, not a variable displacement, a variable orifice, excuse me, meter. Generally, unless you specify otherwise, they become like a check valve if you use them in reverse. And so for this motor application, where potentially the motor's going in both directions, you need to be able to allow free flow in reverse. And that's what you can see by that symbol on there. So just a warning there that if you're specifying a flow meter that's going to see reverse flow, particularly of those style, whether it's a tube meter or the block style flow indicator that we showed, you will need to make sure that's specified to allow the flow back through. So the advantage here is that we want to measure the flow in both directions on this motor, and that's then possible with this RFI reverse flow indicator. Looks very similar to the block we showed before, just allows the flow to come back through. Okay, so the next challenge within Steve's processing plant is he's also got various coolant lines. both with water and with phosphate ester, and he wants to monitor those. So phosphate ester, we've seen fire-resistant fluids used in certain high-temperature applications, maybe more common in steel processing, in ground support equipment and the like, but it has certain properties which mean you have to adjust what sort of instrument you use. So here's two examples of instruments you might use for monitoring of coolant flows. So if it's high pressure water coolant or a water glycol with a very low viscosity, then that unit on the left there is brass unit for water applications. As you can see, very similar to the design of the aluminium one you saw beforehand, still measuring flow, temperature, joule scale, no batteries, using pressure drop to move it, and it has a blanking plug on top, so you could fit a pressure gauge. And the unit on the right is calibrated for phosphate ester. Two main differences there. One, this one has been calibrated for a lower viscosity, sort of 11, 12 centistokes. Secondly, phosphate ester, for anybody who's hopefully not in contact with it, but is familiar with it, very aggressive fluid, should never get it onto your hands. And it also eats through the normal seals. So you can't use it with Viton or Buna rubber seals. You'd have to move to a different sealing technology. And here we use EPDM seals on this. So I guess the principle here is that the same sensors can be used for different applications, just we have to adapt the materials to suit. So one of the further things that Steve's looking at is how can he use sensors to prevent system failures, monitor flow and trigger alarms. So one of the applications is he wants to look at the risk of a runaway load on a winch, but the same principle applies in a few different applications. So here we have what we call the flow hub, the transmitter version, which again is another variable orifice meter. It measures flow and temperature, but it also has a switch inside it, and that enables you then to trigger another device when a certain flow is either a high flow is hit or a low flow is hit. And on the screen you can see the flow and temperature in real time. So it's both a visual indicator and electrically connected to somewhere else in the circuit. And this device, a bit like the RFI, allows the flow to be reversed through it, but doesn't measure it. But the good thing is there, if you're moving a cylinder, you won't lock the flow in place. So if we were to look at that overspeed application in a bit more detail. So overspeeding load creates higher than normal flow rates. We could put a trigger on that. So if we don't have anything in place, we're just going to get a falling weight like that. If we put monitoring in place, we could then use that to trigger a valve to move. That equally could be applied to a lubrication example. So we're monitoring the lubrication flow rates for a large bearing. If that bearing isn't getting enough flow, then that's potentially very dangerous to the life of that bearing. So we could then switch and trigger maybe a redundant pump system to then deliver flow if the first system is failing. So we just look at that in a bit more detail. So there we've got the main circuit on the right, the duty circuit, and the standby circuit on the left. And we're monitoring the flows coming out of those pumps and can then trigger the other circuit as required. Here we've illustrated this with the flow hub units. It could equally be done using the unit that Declan was using beforehand. So this is the compact heavy duty turbine flow meter. Gives you a little bit more accuracy, would allow full bidirectional measurement. And their signal, as we mentioned before, could come out via 4 to 20 milliamp or CAN J1939. Okay, so the last application or challenge for Steve is around using the data that he has to also predict future failures. And with that information, you can crunch the numbers and also look at whether things are starting to fail, a bit like we were before for Declan. So has a motor reached the end of its useful life? Well, on a conveyor motor drive. If we were to switch that on, we have a nice little video here of the ore being moved on the conveyor belt and passed on. We can measure the speed in the motor. If we also measure the flow rate, excuse me. So if we also measure the flow rate, we've then got the opportunity to measure both actual speed and theoretical speed, and we can work out the volumetric efficiency of the motor, and thereby use it as a prediction tool for whether the motor is starting to fail or not. If we wanted to represent that graphically with the efficiency up the y-axis and time along the x-axis, we again can put a trigger and say, okay, when it's reached this level, then it's time to flag that up, switch on a light, set an alarm off, and take a look at it. Okay, so if we recap on Steve's service challenges, had 5 challenges there. Visual indicator pump okay, so we looked at the flow indicator, monitoring motor flows, allowing reverse flow through the indicator, coolant lines, the opportunity to use brass and different seals and things for phosphate ester and water, preventing system failures by building in alarms, and predicting future failures by taking data 4 to 20 milliamp and feeding it into a little PLC and calculating the speed, theoretical versus actual speed. So altogether, Steve and Declan are pretty happy with themselves. Lauren's chuffed because he set them a target to reduce the amount of maintenance time and reduce the downtime, and the 2 projects have come to fruition. So Declan saved his team 3 days a year in carrying out preventative tuning tests on the excavator, because he doesn't have to install anything anymore. He's now got it pre-installed and he can just plug in, take test data and share it. And Steve's happy because he hasn't got service guys going around putting their hands on pipes and going, yeah, it's okay. They're actually using proper instruments to measure what's going on in the circuit and taking real data and making better decisions that way. I said at the beginning that we would just talk very briefly about sort of product selection, tool selection. So if we look at the vast array of different tools out there, whether they're standard or custom, so it could be that we take a tool that we already have, or someone comes along and says, yeah, we'd like it like that, but a bit different, please. We'd really generally ask 3 questions when people are saying, which tool should I use? Why, what, and who? So why is it important that you know that particular measurement? Why do you want to measure flow or pressure or temperature or contamination, whatever it is? And then what are you going to do differently now that you have that information? And I think sometimes that's the challenge. We look back at the case strain monitoring. Okay, the case strain is now 10 litres. Is that good or bad? Is it 20 litres? Is that good or bad? So you need to know, what are you going to do? What's the point when something causes you to take action? And for that, you might need to benchmark what the ideal performance is and then be able to compare it. And that really leads to who you're expecting to collect to interpret the information. If the person collecting the information has a skill level to interpret it, fantastic. If not, do they need to capture that data and then share it with someone else, at which point the data loggers and the transmitters and the like really come into their own, because then we can share the true data with other people. So last couple of slides, there's a few examples from some of the tools that we talked about. So the data logger at the top, and as I mentioned at the beginning, we talk about different maintenance philosophies, but actually these tools are relatively versatile. They could be used for preventive or proactive maintenance. The CTA, there's a QR code there next to each of them if you're interested in looking at the product pages. It could be used for predictive maintenance, or indeed it could be used for preventive, as we were showing it here. We just come along periodically and plug into it. And the DHT, though we haven't talked about it today, is kind of the all-purpose field tool for measuring flow pressure and temperature with a built-in load valve. And some of the other tools that we talked about beforehand, so the flow indicator and the flow hub and the CTA are shown there on the right, which perhaps be used more often on industrial settings. So that's the end of what we had today on how contamination monitoring can save you money. If you want any more information on any of these products, then there's a few QR codes dotted through the presentation, but obviously it's all on webtech.com if you go there. In terms of getting in contact with us, some of you already are our distributors, so you know who we are. If you need to find who our distributors are, then if you go to our website, top right-hand corner, you'll find a distributor. If you're interested in information around the training and the like, there is a section on our website titled Education, and then you'll find a section under that called Further Useful Resources. And I think otherwise, that's everything we had for you this afternoon. Sam, has we got any other questions from anybody?
Thanks, Brian. No, nothing in the chat. Well, there's a statement from Brian. He's interested and would like some more detail. So, in answer to that, Brian, yes, we'll get in contact with you and send you some information. We'll reach out and find out exactly what you're after, and we'll help with that. Yeah.
Okay.
So, well, as we've finished now, if anyone has any questions, feel free to unmute yourself or put them in the chat, and we can answer them. Or say unmute and ask yourself if there's anything. There's another one interested. That's good. We can reach out as well. If you don't want to ask any questions now, then by all means, as Martin said, get in contact with us, and we'll be glad to help. Get lots of hand claps, Martin.
Perfect. Thank you. Yeah, I mean, we've got an email
metrics.
address there. If you know our distributors' details, then contact them. If you don't want to find a distributor, then you can always email us on sales-uk@webtech.com. And keep an eye out. We have another presentation in the making. We'll be focusing on data loggers and the like in the next couple of months, and that'll be out on social media and by email. So
yeah, we'll keep you up to date with that. Okay, well, just to finish off, as I said earlier, the recording will be sent out to you within about half an hour of this, once it processes, and I will send we've got someone else joining. Okay. I will send out a survey in the next day or two. As I said, if you could spare a minute or two, that really helps us. But apart from that, yeah, thanks for joining us, and we'll hopefully speak and see you again soon.
thank you, everybody.
Thanks again, Martin. Thank you.